Today we will be uh, going through like some of the effective knowledge distillation strategies. We will see what is knowledge distillation, why knowledge distillation is needed or why it is used. We will briefly touch upon self-supervised learning. We will see something called as teacher-student framework, and then we will dive into the details of knowledge distillation framework applied to this knowledge distillation applied to this teacher-student framework. Basically, how from the teacher the student learns, and then we will see some applications of knowledge distillation. Now, first question, what is knowledge distillation? So I have taken this beautiful definition from Wikipedia, pretty simple one. Uh, it is the process of transferring knowledge from a large model to a smaller one. So basically, in deep learning, a rule of thumb is you need to have a lot of data and you need to have a big model. So if you have a big model, if your compute capability, if you have the GPU budget, you train as much a bigger model as you can, and then like it is supposed to learn the features in a very higher dimensional space, and it performs pretty well. So that is the rule of thumb. So now these kind of bigger models, they have their limitations. They are slow. Then if you have a low compute machine, low compute system on which you want to deploy this, then these models cannot be deployed there because of your budget constraint, right? So again, like to talk about why is knowledge distillation needed, again, it is difficult to deploy large models on edge devices like your mobile phones or embedded devices. And then knowledge distillation is a very effective strategy to basically match the performance of a larger model using a very small student model. So I will be talking about teachers and students quite a lot during the course of this talk. So teacher is a very large model trained on a lot of data, and student is a smaller model, and we are trying to learn some patterns from the teacher which it has already learned. Uh, we are trying to make the student learn some patterns which from the teacher which it has already learned, right? Now, again, knowledge distillation transfers knowledge from a large model to a smaller model without loss of validity. What it means is the end goal is to try and match the teacher performance. There should not be any drop in performance, or the drop should be within acceptable limits. And then small models are faster to evaluate and more suitable where latency is also a constraint. So we spoke about that. Now, previously, like a lot of work has gone in to come up with effective architectures. Like you have this separable convolution where the multiplication operations are reduced considerably. So you have lesser number of parameters, but you can match the performance. Then there has been like work on like pruning the network so that basically you have a model that you deploy, which is much smaller in size, or you do some sort of quantization to basically extract the useful features that it has learned without much loss of accuracy. But still there is considerable amount of accuracy drop in these processes. We'll see why and how knowledge distillation works so well, and it is able to like basically you are able to match the performance of a large teacher with a smaller model. So to briefly touch upon self-supervised learning, again, the teacher is a very large model which has been trained offline here, and the student is a small model, and you are trying to match the teacher performance. Uh, Now, here you use lot of unlabeled data. So all the images on the left are unlabeled. Like this image you have on the left, this is an unlabeled image. You are getting some pseudo targets, pseudo labels from the teacher. It can be a distribution over a softmax distribution over your n class as well. So those are pseudo labels. Why we call it pseudo labels? They are not hand annotated or human annotated data. These are from the teacher, whatever it has learned before, which is pretty good. And you are trying to match that distribution using some sort of a reconstruction loss. You are trying to learn the student in such a way that the student also is able to basically match those targets. So this is more of use more of this is used more when you have less of annotated data, right? And then again, having said that, the input to the student are like augmented inputs you pass on, and you try to match the distribution there, so that you have the student learns a very general kind of a representation. It somehow acts as a kind of regularizer also. Now moving on, so this is a typical student teacher student framework. You have a, so it is very well represented. The teacher is a big network, the student is a small network. You have some data sources, and you are trying to extract some knowledge from the teacher, and you are trying to pass on that knowledge to the student. So this is how the knowledge transfer works. So this is exactly the knowledge distillation framework, the knowledge distillation what we are talking about today. Now we will see what are the different ways of knowledge distillation, how it works, and why it works so beautifully, right? So again, we briefly touched upon the teacher student architecture and then knowledge distillation. So there are two words, one is knowledge, one is distillation. So when we talk about knowledge, what kind of knowledge can we like extract from the teacher, what it has learned or what it is learning, what kind of knowledge we want to extract from the teacher and pass it to the student is what we are interested in. So one is response based knowledge, the second is feature based knowledge, and the third is relation based knowledge. So I will briefly touch upon, and then we will go into details in the upcoming slides about all these three. So response based knowledge is like, given an input to a teacher model, what is its response? So response can be, let's say we are talking about image classification. So the response of an image classification, if the teacher is a image teacher is meant to do image classification, the response are the output logics, the probability scores over the n classes. Feature based knowledge is again like, so each layer of the teacher will learn some features, right? So feature based knowledge is nothing but the activations. Given an input, what are the activations from each of these layers? So if we can learn some, if the student can learn that given this as the input, this is the activation which I am supposed to get out of the nth layer. So that is what feature based knowledge is. Relation based knowledge is, now each of these layers basically has got some relation between the input and the output. Let's say we talk about a classification, image classification model, and we talk about the ith layer, ith convolution layer. So it expects an input activation, it predicts some output activation, it gives some activation as the output. There is some correlation between the input and the output. If this correlation we can capture in some form, that is relation based knowledge, right? Are there any questions? Because we are going to go deep, slightly deeper now. Are there any questions right now?
Please go ahead. We don't have any questions on that.
Thank you. Now, second thing is distillation. One is offline distillation, but the teacher has learned offline. You use a large model that was trained offline, that was pre-trained, and you try to learn a student from that. Second is online, so where teacher and student co-learns. Third is self-distillation. We will see this in upcoming slides. What is self-distillation? Now, again, we spoke about knowledge. Now, this is a teacher network. We spoke about knowledge, and these are how the knowledge is extracted. If we talk about response-based knowledge, you pass the data to the input layer of the teacher, you get some output. That is the response of the teacher given some input X. So if that knowledge is used to pass on, or if that knowledge is transferred to the student, we call it response-based knowledge transfer. Feature-based knowledge are the activations from the intermediate layers. Here, hint layers are nothing but activation, intermediate layers. And the activations are the features. So if we can learn something from these feature maps and pass it on to the student, that is like feature-based knowledge transfer. And relation-based knowledge transfer is nothing but the correlation between the input and output. So you have something as input going into this layer, you have something as output coming out of that. If you can capture the correlation, you know what this layer as a whole is doing. If you can pass that information to the student, that is relation based knowledge transfer. I will pause for some time so that this diagram is clear and you have some time to see this. Okay, moving on. So first we will talk about response based knowledge transfer. This is a very vanilla setup, but works like first time it was introduced by Jeff Hinton, but works pretty well today also. So this is the knowledge distillation setup. You have a teacher, you have a student, which is usually a smaller size network. Now the idea behind knowledge distillation is when you have a large teacher model, uh, multiple layers might be learning some redundant information. It might be computing redundant features. So you are basically trying to match that performance with a student, which means even with a smaller network, you are able to match the performance of a larger teacher. You are basically optimizing the performance. You are basically optimizing, or in some other words, you are removing the redundancies which the teacher has learned. So in a way, you are able to compress the network, right? The student is a smaller network, it is matching. So with the same with the smaller network, you are matching the same performance as the teacher. So this applies for all knowledge distillation, and that is the beautiful idea behind knowledge distillation. Now the teacher will predict some output distribution, output scores, basically n class probabilities again when it comes to image classification. Student will predict some uh, n class probabilities again. Now, if you have to match this, you need to have some distillation loss, which basically computes or minimizes the distance between these two distribution. Your logits are nothing but a probability distribution across your n class n labels, right? So you are trying to match that distribution label by label. So given an input image, what is the probability that it is a horse, it is a cat? So that score you are trying to match. So that is what is response-based knowledge distillation. We do not care about what the intermediate layers are learning. Only what we are interested in is to match the output distribution. So main idea here is to mimic the final prediction of the teacher model. So going in slightly into the mathematics, this is the residual response-based distillation loss, and it is nothing but divergence loss between the logits, where ZT is the logit of coming from the teacher, ZS is the probability scored across the n classes coming from the student. And this can be, this LR, L subscript R, can be KL divergence loss as well, or it can be a simple dot product. Now, this is from Jeff Hinton's work, dates back to the 2015, but works pretty well even today. So you have a pre-trained teacher model. You have a student that you want to train, which is smaller. So you see the number of layers in teacher and student are different. Like it can be the same, but like usually your objective is to have a smaller student model and train it so that it matches the teacher performance, and you are able to deploy it on some low compute devices. Now you compute the softmax. So here the loss function is basically a combination of your softmax loss across the n class probabilities and your distillation loss, right? So we will see what this distillation loss is. It is again a softmax weighted by this factor T, temperature T. So what T does is, so here softmax scores, you are operating in the exponential regime, right? So if the logits, like the probability for a particular class is very high, what it does is you divide it by an integer value which is greater than 1, it brings it closer. So basically it is not the exact targets, but these are soft targets, these are pseudo labels. So distillation loss is computed against the pseudo labels, and softmax loss, you make it T equals to 1. This is the classic cross entropy loss. So this is the entire loss with which the student model is trained. This is the loss formulation. So LR is again like a response-based loss, and it is basically computing this. It is trying to match this against this, the softmax, I would say, coming from the teacher versus the one coming from the student. And this is the classic cross entropy loss, where y is your labels, the ground truth labels, and you are computing against this. So, uh, any question on this? Okay, so we will go with the limitation, right? So one thing is clear, that we are just trying to match the output distribution here. We do not care about what the intermediate layers are learning, right? So this is one limitation, because given a random input, there can be multiple random inputs where the output distribution is the same. So uh, there is still scope of improvement at this point, I would say. And then since soft logic,
If there, sir, when we are doing the logic-based distillation, is it necessary that data should be same for student as well as teacher? So you can should match, or it's not necessary that you can should be matched.
so we want the sequence to match as close as possible. That is the objective here. In order to
No, no,
match the teacher performance given a
no,
data.
no.
Huh.
No, no, I mean to say data sequence. If we have trained the teacher on some randomly generated data, suppose we have set the random seed and we have just trained the teacher. Now we are training the student by mimicking the features of this teacher. So if the data is different at that time, will it still work?
It will work. The teacher is trained offline. It would have seen maybe a lot more data than what the student is seeing right now.
I mean, we don't, it's not necessary to have a target same.
So you mean the data same or the target same?
The data set, if for example, if I'm training a teacher,
Hmm.
uh, there I have set some random seed, suppose random seed 0, and I have trained the teacher. Now I have teacher there. Now I just want to train the student,
Hmm.
but using that teacher, pre-trained teacher, and I'm setting the random seed something else while distillation. So will it affect the performance, or performance will not get hurt?
Performance should ideally not get hurt, because see, the random seed will be at certain operating point, but then that is not the optimum, right? So that is why you are learning. Even if you initialize the teacher with a different random seed, student with a different random seed, finally the objective of learning is, given the data, given the set of parameters, you need to converge to some optima, right? And here, irrespective of whatever seed we are using, we are trying to match the teacher and the student performance. So that is our
Okay,
objective. Your training,
okay,
given a seed which has already seen some data, your training convergence will be faster here,
okay, okay, fine, sir.
right? Because you are already starting from a point which is already doing good. Like let's say you have a loss curve with respect to the parameters like this. Instead of starting somewhere randomly here, where the loss is very high, you are already starting somewhere closer to the optima, or closer to the convergence point. Right. I'm just giving an idea, because the loss curve is not as simple in neural networks. We are dealing with a much higher dimension, much more nonlinearity. But with a seed, you are already starting at a better point. That's all. So your convergence will be faster. But then the objective of knowledge distillation is to match some distribution from the teacher. Does that
Okay,
answer
sir.
your question?
Yes, sir. Yes, sir. Sir, actually, I'm working on this knowledge distillation, so I'm getting a lot of these problems there. That's why.
Okay. Okay.
Yes.
If you use a random seed, only thing is, you will see initially when you do the knowledge distillation, you will see the loss is very high. It will take time to converge. If you already have a pre-trained student also, and you are using that as the seed, uh, convergence will be faster.
Okay, okay, sir. Okay, sir. Fine.
Now, second, so we talked about like how response-based knowledge distillation only cares about your final layer distribution, the output logics, and it fails to address the intermediate level, whatever the teacher network has learned. And so that knowledge is not getting transferred. So that is one limitation here. And we will see how it is addressed in the later slides. Second thing is, since logics are class probabilities, this is like mostly limited to supervised learning, because you saw here uh, how we need the ground truth y to compute the cross entropy loss, at least in this framework, right? So these are a couple of limitations of response based knowledge, and there are better ways to address this, or better ways to match the teacher performance. So next is feature based knowledge distillation. Now, last time we spoke about matching the output logics. What if we try to match the activations from the teacher and the activations from the student? For the sake of simplicity, if we say that the teacher and the student networks are same, only thing, again, I will take classic image classification as the example. Let's say the teacher can accept an input size of 512 plus 512. Your student is meant to work at 224 plus 224, right? So you are losing some information due to the downsampling. In case of the student, the teacher will obviously perform somewhat better now at each layer. But for simplicity, I'm considering teacher and student networks are same for now, right? You have the same pooling layer and same network. Now, after each layer, if you match the activations, if you try to match the activations coming out of, let's say, after convolution layer 1 coming from the teacher and convolution layer 1 from the student, if you try to match those activations, you are effectively learning similar features, or your convolution kernels will be similar to what teacher has learned, right? Now, how we are going to address the scenario when the teacher is much bigger than student? So that is what we are going to see. And here again, the distillation loss is applied between the activation coming from the teacher and activation coming from the students after each layer, and not to the logics. So here, first thing is, we will simplify this equation. Okay, first thing is f subscript t of x. So x is the input to a layer, and f subscript t is the output activation, right? Same thing for the student. F subscript s of x is the same input is going to the student, and you have some activation coming from some layer. Now, the teacher and the student networks are different. Now we are taking the case where the teacher is bigger, teacher network is different, student network is different. So what is this phi subscript t and phi subscript s is doing is, it is a transformation. It can be padding, it can be upsampling, downsampling. These are set of transformations which are applied so that you have this and this function and this function after the comma. Those are of same dimension. Basically, you are making the two activations of same dimension, right? And then if you have same dimension, you can apply any loss function on that, right? So here we have like LF of L subscript F is the similarity function that we are using to match the activations. These are the transformations that again to basically match the dimensionality or the shape of the student and teacher feature maps. We are applying some random transformations, and these are the teacher and student activations, f of f subscript t and f subscript s. Right? Any question on this?
Yes, sir. Sir, what will happen if we have a teacher and student different? Not in case of architect, in case of like teacher is bigger than student, but when we have cross architectures, I can say a teacher can be a CNN and student can be the transformer. So in that case, we have feature space entirely different. So how can we address that?
So there see now there. So this will be a classic case where maybe cross modal kind of thing you are trying to do. Your teacher has learned some sort of modalities, and you are trying to basically do some sort of cross modality. Your student is trying to predict something else. So you have to have a loss formulation where basically through some transformation, through some choice of layers, after some certain layers, you are trying to match the activation. So let's say we talk about an attention block, right? So attention block has your or like convolution augmented attention block. So what happens there is you have CNN layers to capture the short dependencies, right? You have these activation blocks which can capture the long-term dependencies. Now in an image, you are capturing the global dependencies, you are capturing the local dependencies with CNN also, capturing the global dependencies with this attention mechanism. Now your teacher is doing that, right? Or your student is doing that. Irrespective of that, you are trying to match the distribution. So basically, uh, at the output of a transformer block and at the output of a CNN, right? You expect this CNN output to match what is the feature coming from that. So basically, you are capturing some feature vector, some activation, some sort of features given the input activation. So that is what the objective of any block is, any convolution operation or transformer. It is computing some feature. If you expect the student after this layer to match those features, you are in a way forcing the student to do that here in this knowledge distillation framework, right? So you can do that. There are ways to do that. You just need to have like careful choice of uh, basically loss function. You need to be careful with what kind of transformation you are going to apply, because dimensionality wise they may not match. So you need to apply some transformation to have them in the similar feature space, so that you can apply some loss function and then compute their similarity or dissimilarity. Does that address your question?
Yes, sir, yes, sir. Sir, actually, I was just trying for PCA
Okay.
plus because I need to transform the feature space of both student and teacher because I'm dealing with the cross architectures and I just want to project them into the same feature space. But I don't need to consider magnitude only. I need to consider direction as well. So there is the issue. MSC is not working because that is concentrating on the magnitude. So I tried for LSH. LSH is also not working.
Okay. Okay. So if you do PCA, you will have a change of dimension, so that may not work. Okay, we will get in touch. I'll get in touch with you. Want to know like
Yes, sir, yes, sir.
yeah, yeah. We can take it up after this maybe,
Yes, sir.
or
Yes,
after
sir.
we can surely take it up. I have some ideas, but I need to discuss.
Okay. Okay, sir, sure.
So now we will talk about feature-based knowledge distillation a bit. So again, like deep neural networks are meant to learn very complex feature representations, right? And very generic features, basically. Uh, so output from both last and intermediate layers are used in feature-based knowledge representation. So like in addition to intermediate layers, you can use the logics as well. That is what it states here. And main idea is to match the feature activations. Previously, we were matching the logics. Here we are matching the feature activations. Now, these are the commonly used losses: L2 loss, L1 loss, cross entropy loss, or maximum mean discrepancy losses. You can look for this. L2, L1 are pretty common. Cross entropy is also pretty common. MMD basically tries to basically match the mean in the feature space, mean of two distributions in the feature space. Now, the challenge is which layers of the teacher model to choose to effectively transfer the knowledge. Something similar to what just now she asked, right? Uh, so, teacher is a bigger network. Like, am I going to match the am I going to match the output of the third convolution layer with the first convolution layer of the students? So these kind of challenges are there. Which layer from the teacher I should match to which layer of the student? So that kind of challenge is there. Pretty much experimental. We need to do a lot of experiments, but as a rule of thumb, like nothing can be very generic or stated as a rule of thumb here. Now, relation based, we covered response based knowledge distillation. We covered feature based knowledge distillation. So response based knowledge distillation was again from the output logics. Feature based knowledge distillation is from the activations from the intermediate layers. Basically, we are trying to match that. Now, relation based knowledge distillation, right? Uh, what it does is, like, let's say you have a convolution layer, and given an input, it is predicting some output. It is learning some features. So that given a particular input, it is learning some output. So the relation between, we are not talking about what features it has learned. We are talking about the relation between the input and the output feature maps here. So that is, if you, so previously whatever we talked about with feature based knowledge distillation or response based knowledge distillation, that was just on the output of a particular layer, the output activations of the output logics, right? One drawback from that you can think of is, given a given multiple distribution, you can have an output. Given multiple inputs, you can have an output distribution which is similar, right? So this technique, this approach, what it does is it gives you more control on the knowledge distillation. It says that given this as the input, I expect this as the output, right? So that is what the student should learn. So that is the beauty. It gives you more control, slightly more deterministic, and you are able to basically transfer with much more control, transfer all the gains that your teacher has learned to the student. Again, some small mathematics, but very generic formula. So here what FT1 and FT2 are basically two activations. It can be successive, it can be any other activations. And you are applying some transformation on that activation. Same thing is FS1 and FS2, like two feature maps coming from two different layers of the student, and you are applying some transformation phi of s to that to match the dimensionality, and then you are applying some loss function or similarity metric to basically compute the loss. And while training, you um, compute the gradients on this and you backpropagate. So that is how the student will learn. The teacher weights are frozen till now. We are assuming that they have been pre-trained. Now, relation-based knowledge explores the relationships between different layers or data samples that we spoke about. So IM proposed a flow-up solution method of relation-based knowledge distillation, which is nothing but the gram matrix between two consecutive layers, right? And what it does is it summarizes the relations between two pairs of feature maps. So you have a particular layer, you have something as input, you have something as output. What is the relation between that? And like very simply, you compute the dot product, and then that gives you the relation between these two feature maps, and that is what you are trying to transfer it to the student. So again, like lot of ever since this transformer papers came, a lot of work has been done on attention, and this is like basically you are trying to have some attention mechanism over the activations, and you are trying to extract that information. So this attention will again like basically capture some correlation between your different activations coming from different layers, and that is what you are using as the knowledge to transfer to the student. And again, like the commonly used knowledge distillation losses are expectation maximization, Hubert loss, Frobenius norm. Now, challenges, again, like here also there is a challenge, how to model the relation, like what kind of formulation you want to have to basically have this knowledge relation based knowledge distillation. What are the layers you are going to select? So this is a very generic challenge which is there with relation based as well as feature based knowledge distillation. So we will take some questions. Yeah, we can take some questions now, 1 or 2 minutes, and before moving forward? Are there any or anything we want to explore again, like whatever we have covered till now? Okay. So we spoke about knowledge. We spoke about three forms of knowledge that are used to transfer to the student. Uh, One is
Excuse me,
the, yes.
excuse me, sir. Good afternoon. Uh, I wanted to ask, like, how this knowledge relation-based knowledge distillation, how does it differs from prompt tuning?
From tuning,
Prompt,
you are saying?
uh,
You mean fine tuning?
no, prompt. There are techniques using prompt engineering where the LLM's outputs are used to tune our own models. So, how does this differ from that?
Right. So it is kind of similar. So uh, we will talk about one distillation strategy where what happens is, from the feedback coming from the output layer, you are trying to basically improve your features, improve your network in the initial layers, right? So something similar is what is employed in prompt tuning. You basically the model does some kind of a self learning, right? In prompt tuning, where it fails, it takes that as a feedback, it improves again,
Yes, sir, right, sir.
right? So we will see that. Yeah, very rightfully put. We will cover some sort of a similar thing that happens, a distillation strategy. We will cover that in upcoming slides.
Okay, thank you, sir.
Any other question? Okay. So till now we covered response based knowledge distillation, feature based knowledge distillation, and relation based knowledge distillation. Response was the output logics, had to do with like matching the output logics. Uh, then relation based was basically between the relation of activations which are input to one particular layer and the output to that. So we are capturing that information as knowledge to pass it on to the student. And that is how the student layers will learn that given this input, I need to predict this input. Gives more control, gives slightly better deterministic approach. But then again, and somewhere the response, somewhere the feature based knowledge distillation is intermediate to it. You learn the activations, but you do not basically learn the correlation between the input and the output activations in the feature based knowledge distillation. So moving on, we will cover different distillation strategies. So there is a very good survey paper, by the way, from where like most of these diagrams and I have borrowed. Uh, I have I have it linked here. So basically, so till now we covered the most simplest of cases where the teacher is pre-trained and we are trying to learn the student. That is offline distillation. Online distillation, your teacher and the student both learns together. And self distillation is something similar to what prompt engineering is like. But then like prompt engineering, you have the feedback coming from the output layer and you are trying to pass it on, and you're trying to improve basically the performance of the network. You are adjusting some weights based on the feedback. Here self distillation is your teacher has learned something, and a big teacher, here the teacher and the student are the same. First of all, it is a big teacher, it has learned something, and again, with any big network, it will learn some redundant information, like some redundancies will always be there. So basically what you are trying to do is somewhere towards the like deeper into the network, some activation you are trying to match with the activation of some layer, some initial layers, right? So basically, if let's say again you have a classification network, the nth convolution is predicting some output activation map. You're trying to predict that same map at the n minus 3th layer or n minus 4th layer, just as an example. So what you are doing is you are removing the redundancies there. So whatever the model could have done with 3 or 4 convolution layers, but currently is doing with 5 or 6 convolution layers, you are doing it with 3 or 4 convolution layers. You are predicting the similar. You are predicting similar activations there. So in a way, you are improving the model performance. You are removing the redundancies. So that is self-distillation. So offline, again, we covered this. Large teacher model is pre-trained, and in the second stage you use some sort of a knowledge distillation formulation and you train the student. Online is like both teacher and student models are updated simultaneously. It can be like in a single pass, you first update the teacher, and then in the next pass you update the student to match the teacher performance, or it can be together as well. And whole knowledge distillation framework is end-to-end trainable. So basically you are training both teacher and student. You are doing back propagation and updating the weights there. You can do this only if you have good compute, but a like a good, basically you need to have good GPU budget. But then the advantage over offline is, offline you are seeing the teacher right from, like you have the teacher after it has been trained, so you cannot change those activations. Here you both the teacher and students are learning together. So the effective, like it is pretty effective distillation mechanism, where whatever things the teacher has learned, the student is following that exactly during the entire course of the training. Self distillation is same network is used for teacher and student, but the network uses attention map of its own layers, like somewhere deep in the network, the attention map that becomes the distillation targets for the lower layers. So basically, let's as I discussed, like somewhere at the nth convolution output, the activation map you take, and that is the target for the n-3th or n-4th convolution layer, and you're trying to match that. So again, like you are optimizing the same network in a way to perform better. You are removing the redundancies here. Again, we go back to the same image, distillation schemes. Offline, teacher is pre-trained, student is what is trained. And in the online and self distillation, they are basically trained together. In self distillation, teacher and student are the same model, and you basically optimize the performance, remove the redundancies. Coming to teacher student architecture, like usually teacher model is a big model, student model is what you are learning, and you are trying to get extract the same performance as the teacher by matching, by doing some sort of knowledge transfer, one of the 3 knowledge transfer mechanisms that we mentioned. It can be a quantized architecture. Basically, the models are the same, but they are quantized. Student model is quantized, so takes less space in less memory requirement. It can be the same structure as well as in self-learning we saw, or it can be a smaller optimized structure. Right. So now some applications, again, like model compression. You are not compressing the same model here, but you are having a student model which matches or which is as efficient as the teacher, or even if you have some regression, you are within a budget, and you kind of are you are matching the performance there. So in a way, you are compressing the model. So yeah, that is one of the application in automatic speech recognition. And ASR, again, ASR, you do a lot of sequence to sequence modeling. Same applies to NLP. So this is something which we recently did in our team. And what we had is, so we did not have a full teacher, like which gives you end logics. We had a acoustic encoder, teacher encoder, and we wanted to distill knowledge to the student encoder. Again, one of the mechanisms that we discussed, we used there. It might be published, so I am not going to give more details of it. But then we could get a student encoder, and then when we did the full encoder decoder training with label data, we could get an additional 2 to 3% gain on top of the baseline with this kind of a knowledge transferred student encoder, and teacher was a multilingual encoder. Now, in computer vision, like cross-modal knowledge transfer is like something which has been explored. This is something which my friend in one of the universities abroad is working on. He works on medical imaging. So medical images are very rare commodities, especially for the positive classes. You do not get images. So he's exploring some sort of cross-modal knowledge transfer from segmentation, image segmentation. So if we can basically use one of the state-of-the-art segmentation algorithms and try make that work very well on medical images, which are rare. Like you cannot train end-to-end segmentation network with medical images. Those many images are not there from his domain. But then you are trying to reuse or trying to distill some knowledge from an already trained segmentation network and make it work quite well for medical imaging. So yeah, it is quite in use. And if you have a very difficult benchmark to beat, right? So like in ASR, when we already have student models which are doing pretty well. So to get the additional 2%, 3% performance, word error rate improvement on top of what we already have, a very strong baseline, this kind of knowledge distribution schemes helps. And then like you can also have, like with this ASR example that I quoted about, basically you can distill the knowledge from a much diverse acoustic encoder, like what we did. We distill the knowledge from a multilingual encoder which has seen a lot of data, a lot of audio diversity it has seen, and it worked pretty well when we distill that to a student encoder to work on a particular language, particular locale. So it works pretty well. So these are a few of the references that I looked upon. And any questions?
Hello, sir. Good afternoon.
Yeah, good afternoon.
Sir, you plan to explain more about the prompt tuning versus this thing.
Okay. So in prompt tuning, I have not, like, I do not have hands-on on that, but what I understand is from the user prompts, it is more in the context of a session, right? So the user is communicating, and then from the user prompts, the model itself learns that, okay, I did something wrong and I need to rectify it, right? So that is what prompt tuning is. And self-distillation, here you are not giving any additional feedback from the user. It is more of a unsupervised kind of a mechanism. You do not have any feedback from the user. You do not have any human annotated labels. You are basically, see, your teacher model is large. It is learning some redundant information. You're trying to compress that. You're trying to learn what a layer in a later stage of the network, little deep into the network, has learned. You are trying to mimic that in the initial layers itself. So it is kind of a model compression only. But then again, like ideally, you do not, since the teacher and student architecture are the same, or it is the same network, you do not basically get rid of the memory requirements. It is the same. It remains the same, unlike the offline and online distillation mechanism that we discussed.
Okay, thank you, sir.
Any other question? Okay. So yeah, thank you. I think yeah, I have given back some 5-10 minutes of your time.
Sir, can you share your email ID so that I can have some queries? I can.
Yeah, I can paste here, right here. Okay, I see some questions. Are relation with this? So there is one question: are relation-based knowledge and the model created same? Sir, can you please elaborate that? Are we talking about the student model here?
No, sir. This is I quoted in the beginning, in the first few slides. You have shown the diagram.
Okay, let me.
Can you go to the first few slides?
Yes, this one.
Yeah, still you can go previous one. Yeah, here at this slide I have made that query
Okay.
because this is input output mapping. In model also will represent input output mapping. It's a, I thought both same.
Okay, so this is just the teacher network here, and relation-based knowledge. We are trying to do the input-output mapping. We are trying to do the input-output mapping, like the input layer of the network and the output layer network, plus the mapping between the input activations to a particular layer and the output activation. So, though all these type of mappings we are trying to do and pass that as knowledge to the student. Does that address your question, sir?
Yeah, actually, model is I feel model is represented using neural network here,
Yes.
a deep learning network,
Yes.
and relation based knowledge. Maybe I think this is explainable. Model is being explained through this relation based knowledge.
Right, right. What the model is learning, how given a particular input, what kind of output it is expecting. So that relation is being explained through this knowledge to the student, transferred to this.
Okay, thank you, sir.
And there is one more question in the online distillation. Since both teacher and student are trained together, the distillation loss will affect the teacher model as well, or we will use detached activations or logics during distillation loss calculation. Uh, e- so yes, basically the loss will impact both the teacher and the student. Distillation loss is something which we uh, try to apply on the student. So it is distillation plus, if it is image classification, simple image classification, it is the cross entropy loss. So you have the human labels as well. The teacher learns just from the human labels here. Does that answer your question? So distillation is always from teacher to student. So you are training the teacher using full supervised learning, and the student learns some a part of it from the teacher and a part of it from the uh, basically full supervised learning as well. Yes. Are there any questions? Any further questions? Okay. Thank you so much.